All right, welcome back. So I don't know exactly what this is from, but we were asked to find for which integer polynomials p have the property that the sequence p0, pp0, ppp0, etc. is eventually constant modulo of any number, um, which right away I'm gonna just change that to prime powers. Like suffices to examine n equals p to the e for some e. So is that not like so? Okay, like if p of 0 is 0, then everything is 0. Is that like a sufficient condition? I feel like it, because if you have like, okay, if p is constant, it's okay, fine. Hmm. I feel like if p of 0 is non-zero, then like doesn't feel good. Uh, like the primes that divide that thing are going to not be really happy. Anyways, so is there any non-constant example with non-zero constant coefficient? Uh, yeah, it feels like if p of 0 is non-zero, it feels like it's pretty bad. Um, x to p and e minus x, yeah. I actually wonder if I can for a specific prime p, you can actually bash a real small case out, right? Like in some sense, if I take like p equals 3, for example, then the exponents only matter modulo. Well, also if the exponents only matter modulo 2, other than the constant term. So if you have a constant term, you could like okay, let's do a small case and see what's going on. All right. So like for p equals 3, it suffices to consider p of x equals ax squared plus bx plus c, where c is non-equal to 0, and see what happens. Obviously, this isn't going to do much in general, but I wanted to see if there's at least I can get something. Well, okay, this is. Hang on. Something's. I don't really want to do it, honestly. P of P of P. That's true. I could just like iterate it a lot of times and then say it's yeah. If it's identically Yeah, like, so suppose it's identically, wait, why is 0 so special? Oh, I guess it's the initial. No, 0 shouldn't. Hang on, I'm confusing myself. Like, is it possible for the sequence to eventually be constant to something that isn't 0? Like, if the polynomial p is non-constant? Like, can I have a thing where, like, p of 0 is 1 mod 3, and then p of 1 is also 1 mod 3? That should be possible, right? Like this should happen sometimes. There's no way it doesn't. Like x squared minus x plus 1. Yeah, will eventually be 0 mod 3 forever when you start plugging it into. Yeah. Or sorry, will always be 1 mod 3. So then the question is, like, why doesn't this work for... In fact, this will work for a lot of primes. You could just shift p of x equals qx plus 1. I don't know. Like, x plus 1 is definitely not a valid thing, right? Like, wait, like right now the problem is that the conjectured answer I have is either p is constant or p of 0 happens to actually just equal 0. But that does, I agree, that feels weird to me just because it's like, it feels like it's putting a lot of weight on 0, but I can't find a counterexample to this claim. Maybe it's like if you shift by... No, that doesn't make sense. Does x plus 1 squared minus 1 work or something? If I do that, I'm really confusing myself. Oh my god. Okay, if I put it... No, that just has 0 constant term. What am I talking about? What about, like... There we go. Okay. Yeah, x plus 2 squared minus 2 is a valid solution. Because p of 0 is 2 and p of 2 is 2. So... I should say these are trivial answers, and then there should obviously... Okay, there it is. Which then makes me wonder what the heck the classification is going to look like. So when I expand, this is like x squared plus 4x plus 2 is a solution? No, wait, am I? Hi? Wait, sorry, I'm stupid. What am I talking about? No, this doesn't... This is how you know I haven't... Okay, but here's the question. Is there a polynomial p such that p of 0 is equal to 2 and then p of 2 is equal to 2? That is not constant. Like, such a polynomial surely exists, right? Like forget mod 3. Like, there has to be something satisfying this. Like, p of x equals x minus 1 squared plus 1. There you go. Yeah, okay, there you are. Yeah, and so this is the one where like when you put in 0, the sequence itself is just always 2. And then that begs the question of like, I mean, I'm sure I can get something more complicated than this, right? Because polynomials have enough degrees of freedom, I think. Like you can make P of... You should be able to do something like make P equal to a chain where P of 0 is A1, like P of A1 is A2, P of A2 is A3, or just like here, P of 0 is like equal to C, and then like P of 0 is equal to C is P of C is equal to C. Like sure, I'm sure there must be a polynomial that satisfies this for any value of C. Which makes me wonder if the answer is something like any polynomial that has any fixed point. Like, is it true if I have some fixed point, then modulo P every orbit goes to that fixed point eventually, or like goes to some fixed point? Is that a true statement? I agree. Every divisor of P to the T0 also divides P0. That is. Hmm. Fixed point. I'm trying to think, what's an example of a polynomial that has like a fixed point of some sort, but doesn't eventually go to that any fixed point? Well, okay, first of all, like, questions. Many questions. I have many questions. Questions. If, if P has a fixed point, does it follow any cycle goes to it eventually? I think the answer to that is probably no. And the other question is, are there any examples of P that work even though there are has no integer roots? Okay, yeah, there we go. So the first thing, yeah, 2x plus 2 is good. So it goes to 2, 6, 12, 14, which is, yeah, it cycles mod. Okay, cool. So, yeah, I figured the first one was probably false. But then I have to ask, like, what the heck is the answer going to be? Like, even if I know it has a fixed point, I can't tell if it goes there. But if... On the other hand, I think the answer to the second question is also no. So here's what I'm gonna do. All right, I was worried for a moment about like how fast things stabilize, but there is a bound, and the bound is the following. So let P be a prime. Then the sequence should stabilize within P terms, because the modulo P, the stabilization happens within. Wait a moment. Have I seen this problem before? It doesn't matter. So, for a capital integer n, so for integer n, you need to have that an minus 1 is divisible by like the product of every prime less than or equal to n. And this feels pretty bad, because if p of x grows on the order of cx to the we need a letter for the degree. Let's use d. Actually, no, hang on. The growth is fine. What am I talking about? Do I need prime power? If I keep iterating powers of, if I keep iterating a polynomial, squared, how fast is this? This goes pretty damn fast. It's like 2 to the 2 to the versus. Okay, never mind. I'm stupid. Never mind. Yeah, the growth is fine. AN goes way faster. Even so, it doesn't sit right with me. Like. Yeah, like, even though like the sequence does grow really rapidly, but even so, it feels like it shouldn't grow fast enough for this to work. Okay, this argument does work for linear polynomials, though. Like, if you have a linear polynomial, no dice. Just no. Yeah, then the right-hand side actually doesn't grow quickly enough, because the right-hand side will grow, like, at most exponential in n, but the left-hand side grows faster than exponential in n. The fact that all divisors of p iterated 0 divide p of 0. Oh. Oh my god, are we gonna bring out... We're gonna bring out a hammer, aren't we? I think we're gonna bring out a hammer. Okay, let me first make sure that I understand the thing about. Yeah, let me just kill all this stuff. I don't think we're gonna use it. So claim if if p is a prime dividing p to the n. Well, let's use frick. Let's use t. So your claim is that if p divides two consecutive terms of the sequence, then p divides p of 0, which is obvious. Okay, that's actually just clear. Because it's, well, let's use capital T. Okay, so hence, if p is a prime that doesn't divide okay, let's introduce some notation. We're gonna let RP be a residue the residue modulo p of each prime for which the sequence is eventually constant. And so hence if p doesn't divide p of 0, then RP is non-zero mod p. Which is like almost every prime. So on the other hand, suppose... Okay, but on the other hand, claim if p, let q of x be equal to p of x minus x. So, you know, it's some integer polynomial. If q has no integer roots, then there is a prime for which q has no roots modulo that prime. I.e., if I have a polynomial that doesn't... This is false, isn't it? This is false. Yeah, this is just false. Yeah, x squared minus 2 times x squared minus 3, x squared minus 6 is a counterexample to this for q. Wait, okay, so that begs the question, what the heck is the answer? Yeah, I was going to try to do some Chebatarov density shit, but it's just not true. Like q of x is... In fact, I think there was an Otis problem about this, right? That there's even smaller polynomial. Like x to the 8 minus 16 or something like that? Like the polynomial x to the 8 minus 16 splits modulo every prime. Well, actually has a root modulo any prime. I wonder if I need to use... I don't think that's gonna be good enough though. Thank you, the real Euler for the follow-up. So that's bad. But yeah, I agree it's weird. It's sus that like there's a residue modulo every p for which we stabilized at that residue. And if that we really want that residue to be like the same. Thank you, Signifence, for the follow. We really want that residue to be the same modulo all the primes. That's kind of what we're hoping will happen. I'm not even sure that's true anymore though. Like I can see a world where like for one prime it stabilizes that one thing, and for the most other primes. Okay, so all the same might be too strong, but maybe at least we want like all but finally many primes to all stabilize at a certain R sub p, because otherwise. It implies, yeah, okay, I agree that we might not need. Yeah, you're right that I don't use the fact that it's prime. However, even then, it's just, I don't. Like, what we need is we need to, there's an Rn for every n. Yeah, I don't need P to be prime here. But we would like all but finally many Rn's to line up. Like, we want the Rn's to come together so that there is a fixed point for enough different n's that. Wait, you want to say the fixed points are factors of P0. Wait, what? Hang on. That would be really good if it was true. Hang on. What? Is it true that the fixed point is always, well, it doesn't even make sense to say is like the fixed point modulo n is a residue modulo n. So I don't know if it even makes sense to say that residue must divide. Like, you know, if the fixed point is like 2 mod 3, does that, it's not, it doesn't make sense to say does 2 mod 3 divide 2, because 2 mod 3 doesn't have a parity or something. You could try to say something like if the, like, you take R and then you trap R between 0 and n, maybe, and then try to argue R divides P of 0. I would be surprised if that worked, but it's not out of the question. Q equals 0 mod P0, so 0 is P. It gives you Q, or if R is a fixed point. Oh, yeah. Yeah, it does bother me that having a fixed point is not sufficient, like the 2x plus 2 example shows. Like a 2x plus 2 example has a fixed point. But the problem is that, you know, the particular sequence doesn't actually stabilize there. But even if there is a fixed point, you know, it doesn't promise that your sequence is eventually constant modulo n. Because the fixed point for the 2x plus 2 example is -2, and the modulo 3 that just never shows up. RMM 2019-6 vibes. Yeah, so I think my problem is I don't even know what I expect the answer to be. Like, P of 0, 0 is pretty good, and fixed point is neither is... The fixed point might be necessary, but it's not sufficient either. So I don't know what's going on. Like... X squared minus 2x plus 2 is an example where it's okay, and then 2x plus 2 is an example where it's not okay. But I mean, you can make up examples all day. Wait, actually, hang on. Can I just like oscillate? Like, okay, hang on. I think, hang on. I feel like I've been going about this the wrong way. I really want to go the other direction, where I start from a sequence and pray. By which I mean, we're going to... See, now I want to put the 0 back in. But let's put the 0 back in. It might actually matter. So, like, if P of 0 doesn't divide P of 0, we're screwed, right? Because it, indeed. So claim... Yeah, I was just looking at the 3 again. I was like, wait a minute, what am I doing? If P of 0 is not equal to plus minus P0, then let n equals P of 0. N is double P of 0 to get a counterexample. I think this is the game we should be playing. It's like start with the sequence and then try to generate bad n. And then for almost every polynomial, unless something very specific happens, yeah, so in fact, what does it mean for P of 0 to divide? Oh, let me keep the list of examples out. So examples. Well, we'll write interesting examples actually. I was supposed to think, like, what examples are some good data? Which is, so constant and P of 0 obviously work. And then we saw x squared minus 2x plus 2 works, writing off the fixed point P of 2 equals 2, since P of 0 is equal to 2. And then P of x equals 2x plus 2 shows the fixed point is not enough. Fails modulo 3. But on the other hand, like, if, like, I applied this polynomial and I got something that was, does that happen? Like, is that a thing that can happen? That doesn't happen, right? Like, it's just not okay. Like, let n equals P of 0. So, like, you look at the, literally, you look at the second term, and you're like, the second term is equivalent to P of 0, is equivalent to m, is equivalent to 0 mod m. But on the other hand, this doesn't happen. Like, if P of 0 doesn't happen to divide m, like, if it's a larger multiple of m, then you look at it modulo that thing. So in fact, we need P of 0 to either be plus or minus P of 0 for this to even be possible. Which rules out the 2x plus 2 that was causing us issues earlier. Yeah, so the 2x plus 2 issue goes away. And we see that so if P of m equals m, you're definitely okay, because the sequence then reads 0, m, 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 m. And so the only other question I have is if P of m, remaining case, if P of m is equal to minus m, what happens next? And what you say is the sequence has started 0, m, and then minus m. And I guess... Are there any examples that look like that? The world may never know. 1 minus 1. Why does this feel so bad? I feel like I should just be able to... Yeah. So if P of minus m is equal to minus m, then the sequence is minus m forever. But by the same logic, we need P of m, like the third term of the sequence, to divide m. Otherwise, take modulo it. We get a disaster. Because it will be a multiple of m. Like every number in the sequence is fated to be a multiple of m now. 3 cycle modulo it. So if P of minus m is equal to minus m, then the sequence is minus m forever after, and we're all good. If P of m is minus m equals 0, contradiction, and if P of minus m, I guess 0 doesn't. 0 is a different case. We don't have to. Sorry, modulo 0 is different. If modulo 0, if n equals 0. Yeah, so if you get another 0 in the sequence, then you're screwed, I think. Because then the sequence is legitimately periodic, and then... You know. And the only other case is, you know, if it oscillates between m and minus m, it's also a contradiction. So I feel like this means that, like, answer, either P of 0 equals... Either P of 0 has to be a fixed point, like P of 0 equals P of 0, or P of 0, or P of 0 equals minus P of 0, and P of minus P of 0 is a fixed point. And the only question I have is, does the second case actually happen? Like, is there a polynomial P? And I feel like there probably should be. I don't know. Is there a better description of this set? Like, I feel like normally when you do a math contest, like when it says find all, there's sort of this implicit promise that like when you find the correct description of the set, it will be extremely obvious that it's the that you cannot give a better description. Like you might get the answer n is prime, and like there's no better description of prime. Or you might get a finite set, and then you write down the list of elements. Or you might get like set of even integers. But here I'm not actually sure whether I'm done. Like, I don't think there's a better way to describe this thing because there's shit like x squared minus 2x plus 2 that works. But I legitimately don't. Well, okay. It's like p of x is like x minus a constant plus a constant times any other polynomial. There, that's obviously a final description. You can't do better on that. Oh shit. Hang on. No. Yeah. But I don't know about, like, does the second case ever actually happen? Can you get P of C equals minus C, and then P of minus C equals minus C? I want to say you can. Okay, so first I need like P of C to be minus C. So it looks something like this for some C. I'm like switching between C and M interchangeably, which is a little bad. And then I need minus C to stay minus C. But hang on, I fucked up. X minus C. Sorry, this one has 3 different conditions. Okay, the first is P of 0 is minus C. The second is P of C. No, hang on. P of 0 equals. Oh, fuck. There's a description. There is some description, and it's going to be super annoying to write. Oh, fuck. Let me do the annoying condition. So like minus C has to go to minus C. Actually, there might not be many cases where this happens. Fucking heck. So, okay. We know it has to take this form. Because it's like, okay, like, P of C and P of minus C are both minus C. So P of X plus, well, yeah, it should be like S plus C, X minus C times something. And then you also know, and plug in X equals 0 now to get 2C equals like Q of 0 times minus C squared. So there's like a small finite number of cases where this can happen. I don't really want to work them out. Like 2. Like C equals 2 plus minus 1 plus minus 2. And then like, this is obviously you cannot get a better description than that, I think. Like you pick a value of C, and then you like QB any polynomial for which the constant term happens to equal exactly 2 over C. So I think that's a final answer. Is there anything else to say? Yeah, C squared divides 2C, so it's like any of C equals plus minus 1 plus minus 2. And I don't think I think that's a final description. I don't think you can do better than that. All right, we're done. Yeah. Yeah, so I was right, the third case doesn't happen too much, but it still happens quite a bit. It's like, you pick whether you want C to be plus minus 1 or plus minus 2, and then you, Yeah, okay. Yeah, C is bounded in the triple case. It's not bounded in the second case, in the like 0 CCCC case, because you can literally just. I mean, I gave a complete this is a complete description. Okay, cool. Let me just write this up. The quantifiers are kind of much. What's the source of this according to AOPS? Is there Malaysia TST? Or SST? Wait, what is TST or SST? What is SST? Wait, okay, now I need to know whether that's is a typo for TST or it's a different contest. Okay, so we're going to postpone writing the answer because the answer is really annoying. The main claim of the problem is the following: is that the sequence must take is can be the sequence is either 0 0 0 0 0 C C C 0 C minus C minus C for some integer C. Yeah, and proof. If p of 0 is equal to 0, we're done. Oh, this is a fancy version. Then every term in the sequence is a multiple of C by working modulo C. On the other hand, every term must divide C. Indeed, if some term in the sequence is a multiple of C that is not plus minus C, then taking modulo M. Well, actually, just IE must equal plus minus C. If some term M in the sequence is a different multiple of C, then take modulo M to find the sequence is not eventually constant. Modulo M. Okay, and the claim just follows from this. Yeah, this is why you don't do the fancy crap. I was trying so hard to do like Trevitarov magic, and then other people were bringing up random arrows problems, but also it's just this is what happens when you know too much stuff. you miss the really obvious thing that's right in front of you, namely that literally you look at the second term of the sequence and it has to be one that you shit. Also, I put the brakes in the wrong place. God, I was trying to use Chebatar of density. Shame on me. Just literally look at the second term of the sequence. It is already good enough to do almost all the work. Actually, I'm going to drop the condition C is non-zero, because we only use it in the proof. It's actually easier if I do it this way. C and Z. Polynomial form, X. What did I say it was? Q of I needed Q of 0 to be like cease like I need like fuck. P of 0 had to equal C. So it's like 2C over minus C squared. Hence C in plus minus 1 plus minus 2. For some C, which is equivalent. Okay, I think that's literally it. Yeah. Wow. Way to get baited. Because literally, like, if you look at the this is the main work, and we looked at literally like even though I stated this M thing for any time in the sequence, in truth, you actually only need to look at like the first like 3-ish terms. Like you actually, like, even though it's an eventually constant thing, like if you look at like the first 3 or 4 terms and do cases, that's literally all you need to do. You don't need most of the terms in the sequence at all. It's just all bait. Yeah, I got duped. Was not paying. Well played. Yeah, I'm gonna write this a little more. XRX minus frac 2C. I think that's a little more obvious that it's a final answer. Actually, no, let's keep it the way it was. It's harder to read that way. Okay. I feel like I'm supposed to classify this as a number theory problem. It's a little... I don't know. I definitely went down the wrong rabbit hole for a while. I was trying stuff that was way too fancy relative to what I needed. Wait, why did I write arrows? We literally just explained it's not arrows. I think the answer is hard to come up with, but squad selection test? Really? They call it a squad selection test? Wait, where did you find that? The only possible polynomial is 0. Oh no. Oh, I see. Can I just write TSD so that I don't have like 10? I'm already worried that my database has this alphabet soup where like every contest has like this different abbreviation, and I was like, alright, well, we'll respect the contest organizers and use the correct abbreviation. But also, oh my god. Squad selection test. What a concept. Yeah, TSTST is definitely a worse name. I honestly think that my... Oh god. See, the problem is if you use squad selection test, the problem identifier doesn't get detected automatically. Like, I would need... Okay. I would need another edge case in the like PUID detection algorithm. Oh yeah, okay. No, there's a TST and then an SST, and it's actually oh my god. There's team selection test and then selection team for the squad team in year N+1. You know, I really think this is all the US's fault, isn't it? Is it? The stupid 2-year thingy. Oh my god. I'm pretty sure the US was the first country that had a test whose official name was literally TSTST, and then after that I saw like things quoted as China TSTST and like German TSTST, and now we have Malaysia STST. So I don't know if it's our fault, but we were the first one, and it doesn't bode well.